Welcome, dear students. Today we're gonna learn about the human eye, the optics of human eye. All right. You might have think that it's kind of biology topic, but actually it's not. All right. First, we are gonna know about the parts that are involved in the visionary ability of human eye. All right. So first, we're gonna look into cornea, which is actually a lens, the outer lens of the eye. Then comes the lens. Okay, just simply the lens. We call it the lens, but cornea is also a lens. All right, there are two lenses in our eye. Right? The spacing between cornea and lens is filled with a liquid that is called aqueous humor. Okay, or aqueous humor. So this is a just a transparent gel-like substance, right? And the refractive index of aqueous humor is 1.337, right? Now comes to the muscle which adjusts this lens is called ciliary muscle. Ciliary muscle, and this little part which just adjusts the incoming light that falls on the lens is called iris. Okay, this part. This is called the iris, which adjusts the amount of light that strikes our lens. Okay, you already know that this part is called retina, and this is called the optical nerve. Optical nerve is the one which takes the optical information from retina, converts it into the electrical signals, and sends it to the brain. This whole part of the eye is filled with a gel-like substance which is called vitreous humor. Okay, vitreous humor. And the refractive index of vitreous humor is just similar to the aqueous humor, right, which is 1.337. The refractive index of aqueous humor is 1.336, and for this it's 1.337. So there's just a little difference between the refractive indexes of vitreous humor and aqueous humor. Now comes the physics here. All right. Now, if we just take this eye, both of these lenses play a role in the refraction of light and production of image at this point. Okay, at the end point of the principal axis here. Alright, this is where the image is formed. So when parallel light rays falls on this cornea like this cornea acts as a convex lens. Alright, and it just converges these lenses into a single point, which is the focus of these two lenses, right? Which is the focus of especially this one. This is the focus of this lens, right? After just striking the walls of this lens, these rays get refracted and will start traveling this direction. After striking this lens, they again get refracted and they would just start traveling in a certain direction where they can meet one another at the retina. This is the point where the image is formed. Okay, so just retina takes this image, takes this optical information and converts it into the electrical signals and send it to the brain. Now, what we see that the cornea does major of the refraction. All right, why does it refract more rather than the lens? Of course, because cornea is a thin lens. You can see it has a very thin layer here. So the thinner the lens, the more will be the refraction. And again, you can see here the refractive index of aqueous humor is 1.336, and the refractive index of air is 1.00027. So when we try to find out the angle of refraction by Snell's law, we would get N AH for aqueous humor divided by N A for air. Okay, so this angle would be much higher. Why? Because there is a great difference between this value and this value. So the ratio between these values, okay, would be higher as compared to other devices. Okay, so it acts as a kind of refractor here. This aqueous humor acts a kind of refractor which refracts these lights and focuses onto the lens. When these lights get to the lens, they are converged, right? But not so much. They won't be able to just converge at a single point yet, right? The lens further refracts these waves and then focuses them to a certain point, which is called the focus, and this focus lies at the retina. Right? Now I will come to your book now because it has a clearer diagram here. Alright, you can see this is the cornea, this is the vitreous humor, the lens, the iris. Iris is this small, you can say, little muscle which just contracts and retracts when the light enters, so that the amount of light coming onto the lens could be just arranged, somehow rearranged, right? This is aqueous humor, this is vitreous humor, this is ciliary muscle, optical nerve, and retina. I've told the function of these to you. All right, now what happens when we see an object at infinite distance as compared to an object as a distance close to the eye? All right, first, considering this image, if an object is just lying at an infinite distance, what happens is that, for example, here consider we have a tree, okay, at an infinite distance, just very far away from the human eye. All right, so the light coming from here would be nearly parallel to each other. Okay, as they are nearly parallel to each other, they will strike the lens at the same angle, and you can see they're not coming from an angle more than 90. Okay, they're coming at 90 angles, right? So they would get refracted perfectly towards the retina, and they will meet each other at retina. Okay, all the light rays would meet each other at retina. But what happens if, you can say, less distance or a closer object is seen by the eye? What happens here? It would just strike this lens again and gets, these lines get interfered at the retina. They will meet one another at retina, which is the focus of this lens. All right, you might have noticed that in this case, this lens is much thinner than in this case. Why does it happen? All right, you can see that here the lens is thinner because we don't want any more refraction here. The outer layer of the lens is much, you can say, flatter than this one. This is a more curved surface, right? As the surface is more curved, so it would refract much more than the you can say plane surface. Okay, this is almost a plane surface which refracts a little so that the light would get bent and would focus at the retina. But in this case, there is a much greater curve in the lens so that it would get refracted much more. Why do we need a higher refraction in this case? Because in order to converge this light ray from this light ray, there is a lot more angle between them. Okay, the angle between them is a lot more, so we need to converge this line way more than in this case. Okay, you can see the angle compared to them is much less than the angle as compared to when the object is near to the eye, right? So in this case, we don't need actually more curved surface here, all right? But in the case when the object is near the eye, we need a surface, we need a lens that is more curved, that can refract more as compared to the distant object. All right, clear now? Now, coming to the point, the closest distance at which I can focus clearly is called the near point. What exactly is near point? The closest distance at which the eye can focus clearly. And its value is typically 25 centimeter for a young adult. Okay, so it is the point after which you will start to see a blurry image. Okay, you won't be able to focus on an image. For example, if you just concentrate on your hand, take it closer to your eye, you can see also in the camera it will just start to blur the image. All right, so the closest point where the image can clearly be seen is known as the near point of the eye, right? Or near point of any lens, of course. Okay, so in young adults it's 25 centimeter, and of course in the older persons it just increases its length. Okay, so as we get older, the near point also gets increases, so that we won't be able to see things that are very near to us. Okay, young people can see very the things clearly when they are very near to them, but the older we get, we won't be able to differentiate between the light rays coming from the different directions. Therefore, near point would get farther from us as we get older. Right? Okay, now what is the farthest point or far point? We know about near point, the closest point at which we can see an image clearly. But what exactly is the farthest point? Right? Farthest point is the farthest point at which we can clearly see an image. But this farthest point is taken as for a normal human as infinity, because we can see farthest images very clearly as we can see the stars and the moon, and so it just determines that we can actually see objects up to infinity as long as the light reaches us parallel to our lens or the cornea. Right? Now coming to some defect that many humans have: short-sightedness and long-sightedness. Okay, if a human is not capable to just detect this light ray at its retina, then what would happen? What happens if these light rays would just meet one another at a point which is farther from the retina? Or what happens if these two lines meet at a point which is just closer to the lens and away from the retina? Okay, in both the cases we won't be able to see the perfect image. Okay, the most balanced image, the clear image. All right, in this case we will have to adjust some kind of lens in front of our eye in order to provide the required convergence. You will see it. In short-sightedness, the human eye can focus only on nearby objects. All right, so if we can clearly see the nearby object, we won't be able to see the object that are far away from us, then we are suffering from short-sightedness. And vice versa, if we can see the objects which are very far from us, then in the case of the objects which are nearer to us, then we are suffering from long-sightedness. Okay, so what are the measurements we can take to just remove or get rid of this short-sightedness and long-sightedness? All right, first, why does short-sightedness happen? Short-sightedness means that you are capable of seeing the objects which are nearer to you but you can see the objects that are far away from you. Okay, it means that the ray that strikes your eye meet at a point which is just in front of your retina, but it's closer to your lens than the retina. All right, so what happens here is that your iris becomes too large and it won't allow much of the rays to get converged to the retina. Okay, it would block your retina, your lens. Okay, so there won't be much refraction over here, and we would again get the focal point between the retina and the lens. All right, you can see here these would get refracted, but there won't be any much area so that they can get refracted at the retina. So they will meet at point between retina and the lens. So how can we just get rid of this short-sightedness? We are gonna just do one thing. We're gonna introduce a concave lens here. Okay, if you've seen a just concave lens, at this concave side is just one side of the lens and the other side is the plane area, because we don't actually need that much refraction over here. Okay, so we are gonna use the lens which has its concave side, just one concave side. All right, what it would do, it would just converge, it would just diverge the incoming light onto our lens. All right, in this case, when the light get diverged, it would reach our lens properly and equally in all the directions. Okay, so that it would again just get converged to our retina, just like in the case of a normal eye. All right, so why does this short-sightedness happen? You can see in this diagram our cornea has just bulged up a little. As this one has bulged up, what happens is that it just try to converge more light. Okay, and it just tries to converge more light, so the power of this lens increases. As the power of the lens increases, the focal length decreases, and as the focal length decreases, the image would be formed just you can say nearer to the lens, right, and away from the retina. But if we introduce a concave lens which diverges these rays, okay, so the cornea would just adjust these rays in a parallel manner, and then the lens would do its job and converge this kind of rays onto the retina. The opposite case is with the long-sightedness. Right here we see that there is a flatter surface of the cornea. As it has a flatter surface in long-sightedness, the rays won't get much refracted as they should be. You can see these rays are actually traveling, in a straight line here. The cornea won't be able to refract much more of the incoming light, and after striking the lens, the light would get converged to a point farther than the retina and the lens, of course. Okay, they will meet at a point away from the retina and not on the retina, so the image formed here will be very blurry and not really focused well. Right, and we can remove this long-sightedness by just introducing a kind of convex lens. Okay, but this is a plane of convex lens. One side is plane and the other is convex, so that these rays can be converged much. Okay, as our cornea could not converge it much, so we had to introduce an external lens so that it could work with our cornea and converge all of the light to a single point called the retina. Right, this is how we can resolve the issue of our long-sightedness. Next point is resolving power. It is nothing, it's very simple. Okay, resolving power is the capacity of an instrument to distinctively separate two points which are close together. Okay, if you are able to just distinguish between point A and point B, then we have a strong resolving power. If we cannot just distinguish between these 2 points, then we have a less resolving power. Coming to our diagram, you will understand it much faster with it. Just take a look with this at this point. Okay, in this case, we are gonna just think that if this is a single source of light, okay, because it seems like a single source of light here. Why? Because it is very far away from us. Okay, as this light and this source of light gets closer, you will be able to distinguish between these two sources of light. Okay, this one is a separate source and this one is a separate source. Okay, so this is called the resolution power. If a person can easily distinguish between these two sources, then he has a high resolving power. And if he won't be able to distinguish between these two sources, he will see something, a kind of source like this, and he won't be able to resolve it. He won't be able to distinguish between these two sources. Okay, so he will definitely have a low resolving power. Okay, so a person with high resolving power or an instrument with high resolving power can easily distinguish between two sources like this one, and a person with or an instrument with a low resolving power would not be able to distinguish between this point and this point, and he will be able to see a single source here. He would think that a single source and the light is coming from a single source. Okay, so this is the resolving power, and this is how an instrument is, just we call an instrument if it has more capability of resolving different sources of light, and if an instrument cannot do so. This is a property of the lens of the instrument. All right, the lens of the eye, you can see the lens of the eye, or the lens of any other just optical instrument. You can say camera, or a microscope, or a telescope, or any other instrument. Right, so this was all about, you can say, an optical instruments for today. We are gonna learn about angular magnification and super microscope in our next lecture. And thank you so much. If you have any question, you can just ask me freely in the chat. Thank you so much, everyone.